So to start, the purpose of this lab is to show the relationship between kinetic, gravitational, and spring potential energies when a mass is oscillating and attached to a spring. What we will see is the observed position, which is a real-life simulation made through Tracker, and a predicted position, which is the online computational model made through GlowScript and based on the Tracker's X and Y position values of the center of mass. So, to continue the intro, some models and fundamental principles used in this lab are Newton's second law, and it is intrinsic to this law because it states that F net is equal to the spring force plus the gravitational force. And then also the energy principle is very important to this lab because it shows that the system's change in energy is equal to the change in energy of its surroundings. So if there is no change in energy in its surroundings, then all of the system's change in energy will be equal to zero. It would be total energy is equal to zero. Change in energy. And the brief preview from this lab 4 is that each of the potential energy components will add to zero and show a constant change in energy equal to zero, thus proving the energy principle to be true. So some of the different potential energy formulas I used in this lab are the spring potential energy, kinetic potential energy, and gravitational potential energy formulas, and it's because each of these potential energies are intrinsic to this lab. So some assumptions before even getting started are that the addition of each of the potential energies will equal zero since there is no work done in the surroundings. And that's because we put everything in the system. So the system is the spring, ball, and the earth, and the surroundings are equal to nothing. And so some initial conditions of the system are that the velocity is equal to zero, and you're going to see that in GlowScript, as well as the initial position are these values here. Some of the details of the experiment, well, I first used the recorded video of the oscillating spring, and then I took that video to Tracker, where I observed the location of the center of mass at different timestamps in Tracker. Then I used GlowScript in VPython to create a computational model of a ball attached to a spring, and I used the potential energy formulas I mentioned earlier to equal the total change in energy, which will be 0 joules. I also used Google Sheets to insert my Tracker X and Y data, and I used the Google Sheets file for the GlowScript model to compare these Tracker values with the computational changes in energy. So first, the observed position, observed version in Tracker is shown here, and the center of mass is shown in this video. Cool. So some GlowScript code that's really important for this is you can see on the right the spring constant and the relaxed length of the spring L naught. I found those values by first finding the oscillation period. So I found K by taking the timestamps of an oscillation period, 3 of them, in the Y direction, and then I used that to put into the formula where K is in the oscillation equation. And then once I found K, I put that into the Fg plus Fs formula to find F net, and you can find L hat, or you can find L naught from the finding K in the other equation. So I listed out what I did there. And then more about the GlowScript code. Each of the potential energy formulas to the right are going to equal to get delta E, which we will see at the end. So overall, some big results from this lab are that there is a change, especially near the end, in the X position values between the computational and experimental models, and this is really because of the drag force. And what this model is showing is that the system is not isolated from its surroundings. Now, some possible sources of error. There's always human error. I may have not made the center of mass perfectly in the middle. And also, other errors include when starting the position, maybe I was off and making sure to start tracking the data as soon as the man drops the ball. And so what does it mean? Well, the first question is the energy principle satisfied? And yes, it is. This graph to the right shows that each of the changes in potential energy equals 0, and no external forces are acting on the system. There's no work done. So, yes, delta E here is equal to 0. And second, what does it mean question? Well, when looking at the x and y directions to find k, we see that it's different because the oscillation time intervals are different. And they will produce different time periods for one full oscillation.